we're going to go ahead and get started. We're running a little bit behind, and while we're going here, I'm going to connect a little clicker here. Food is supposed to be on its way, and so when it gets here, we'll take a little pause and let you all pick up your food. And I'm sorry that it wasn't here already, but sometimes these things happen and are unavoidable, so we'll just do the best we can with it. So we're in business. Okay, so all right, so first off, thank you for coming here today. My name is Chris Rakes, and I'm going to be talking through a little bit about structural equation modeling and confirmatory factor analysis. This is our third session this year on this advanced research sessions, and the food is here, so we'll be taking a break here in just a second. So basically, I'll give you an overview of what we're going to do. We'll take a quick break while everybody grabs the food, and then we'll move along. So if you haven't been here in the past sessions, let me talk very briefly about what I mean by advanced research and why are we doing advanced research. Or why are we talking about it here? So by advanced research, we're talking about a lot of the statistics that happen after multivariate statistics. And so one of the things that came up very early on in my career was the knowledge that if you stop where most doctoral programs require you to stop, or don't require you to go further, you're at multivariate statistics. And if you stop there, you don't understand anything that you've done well enough and don't have enough experience with it to really use it, and you don't know any of the stuff that you really need to know to put everything else into context. And so my goal in setting these workshops up is to sort of give an introduction to these topics so that you all become aware of them at least, and can frame some of what you do know and explore things further as they become important to you and to your research. One of the things that I work really hard on is trying to explain some of these advanced topics in a way that would make sense to anybody. And so I sort of figure at the very outset that if there's a way that makes sense to me, everybody will understand it. And so so it's sort of advanced statistics for researchers from a guy who doesn't think in any sort of advanced ways to begin with. And so I'm going to try to sort of lead you through some of the ins and outs of how these things work, all the way through to where we're actually doing something fairly advanced, and we didn't even realize that we had left all the basic stuff behind, and then we go back and pick that up and sort of put that into context and make it make more sense. So with that today, we're gonna go into some basics. Confirmatory factor analysis is sort of the simplest form of a structural equation model, which is why that's this session. We did an intro to both SEM and meta-analysis on this first session. Second session, we went a little bit deeper into meta-analysis, and sessions 3, 4, and 5 go deeper into structural equation modeling, or SEM. And so we're going to talk a lot today about variance. And everybody in the room is probably thinking, well, I know what variance is. And yet, if you actually had to put a definition on it, you might find it difficult. So the food is here, so why don't we go ahead and take just a couple of seconds and grab some. It's in the back there, so please help yourself. To those of you who are joining us from somewhere else, thank you and welcome, and we'll just take a brief pause and then we'll get right back to it. And thank you for your patience. Okay. So if you're going to understand advanced statistics of any shape or form, it's going to have to be connected to the basic statistics. And so I'm going to start right back at something probably everybody in this room and anybody who's watching can just quote right away without even looking at the screen. We've got these 4 types of variables that they are nominal, ordinal, interval, and ratio. The nominal variables are the ones that are just names and descriptions, their categories, their locations, their name, you know, that kind of a thing. Your ordinal are ranked, so first, second, third place kind of a thing. And remember that one of the differences that separates ordinal from interval variables is that there's no assurance that ordinal variables have an equal distance. So first and second place might be the same distance from each other as second to third, but first and second place might have been nearly a tie, and third place might have been trailing in the distant horizon. And so ordinal variables have ranks, but they don't necessarily have that guarantee of an equal interval. If you do have the guarantee of the equal interval, then you're really dealing more with an interval variable. And in an interval variable, you can have dichotomous, so just yes or no, 0, 1, or you can have polytomous, which your standard Likert scales, 1, 2, 3, 4, 5, those kinds of things. But the difference here, or the important feature here, is that there's no absolute 0. So in other words, if I give you out a survey and I have strongly disagree to strongly agree on a 5-point scale, it really doesn't matter whether I number it 1 through 5, -2 to +2, 10 through 15. It just doesn't matter because the real difference is the comparison there. But in ratio variables, our measurements, our scalars, there is an absolute 0, and that number means something very different. 1 inch high means something very different than 1 foot high, and so on and so forth. And so typically, the higher on this list you go, the more you can do with the variable. And there are a lot of issues that come up in statistical papers about people doing things with a variable at one level that really belong with another level. For example, treating an interval variable like it's a ratio. There are actually a lot of cases where that's fine to do, and there are a lot of cases where it's not fine to do. And so it isn't a matter of yes, I can or no, I can't. It's a matter of you got to really be careful. So for example, one of the places where it's really never okay to treat an interval variable like its ratio is when it's dichotomous, because there's no way in which it can have any kind of a normal scale. That's 2 distinct features. 3, again, going to be very hard to get away with that. 4 categories tends to get a little bit easier. And a lot of what I've read says that 5 categories or more is usually a little bit easier to justify, that those usually are some sort of a continuum. There's disagreement with that. I've actually read some papers dating back all the way to the late 1970s where they say, if it's an interval variable, what do you do in treatment? Like it's a ratio. And in structural equation modeling, there are actually special matrices for dealing with interval variables as interval variables, not ratios, which is fine. They're really important to do, and so on and so forth. But the first thing that you need to understand is that these different characteristics of these variables that you learned from probably your very first stats class really have big ramifications on what is valid and what is not valid in terms of statistical inference. I actually once saw a novice student take a nominal variable, student ID, and actually did a linear regression on the ID numbers because they had listed them, they had done them, you know, just sequential 1 through 100, and it looked like a nice linear variable, so that they weren't really thinking about the type of variable and they just ran off with it. You don't see that very often. Novice, it's a student, whatever, but you do have to be careful. So when we are describing data, we usually think about trying to represent the data somehow, which makes sense because if you have a list that's a mile long of data points, you can't describe every single one of those data points. And we usually start by thinking about one of the centers. And there are 3 centers to think about. So to start with this, I want to go with an illustration. And so I just picked out a 7 data point set. And there's nothing special about this data set at all. So first thing is, if I put this on a number line, here are my points. I've got my my 1, my other 1, I have my 50 way up here, and so on and so forth. So by putting them on the number line, I've plotted them in ascending order. One of the first centers that we typically think about is that mean. We just add the numbers up, divide by how many there are. We have the 16.3, and that's right here on the number line. We have the median, which is not the center value, it's the center term, regardless of what the values are. So in this case, we have that 0.10 puts 3 data points to the left, 3 data points to the right, and so my median is 10, which you'll notice is a little bit left on the number line to the mean. Mode is the most often repeated term, which in this case is 1. So this is a data set where we actually have 3 very different numbers that come up based on whichever center we chose to look at. Without any sort of context, I can't decide whether mean, median, or mode is a better data point in this case. For example, it could be that these 1s are an aberration, that somebody didn't actually fill out something correctly. It could be that this 50 is the aberration. Depending on what the context is, I'll have to make a decision about which one of these numbers is the best one to represent the data in this set. Then we enter this notion of degrees of freedom. The first thing that we have to understand about degrees of freedom, it is the number of independent observations, which doesn't mean a whole lot in terms of sample, except in a few cases, but it means a lot in terms of our population. So think about another illustration of a group of 4 observation whose mean is 20, which then means that the sum is 80. If x bar is 20, we automatically take that sample mean and we assume that it is representing the population mean, so we estimate mu to be 20 also, which doesn't mean a whole lot in a group of 4 observations, but this is just an illustration. In the next sample, we've already estimated the population mean to be 20. So then, if we took another set of 4 data points, they need to sum to 80. Otherwise, they don't give us a population mean of 20 anymore. The first 3 observations are free to be anything, but then the 4th has to be fixed. So we got 3 free ones. I can make it anything, anything, anything. Then whatever that sum is, this last number has to be whatever will make it be 80. Okay? In other words, it is no longer an independent data point. Once I have estimated my population mean, I no longer have an independent data point at the end. It's dependent on whatever the other values are to get us back to that population mean. Now, you can argue very validly, I think, well, how do we know that it isn't one of these 3? We don't. And how do we know that this one was right and this one wouldn't be different and this one's not just as valid and could be a better estimate of the population mean? We don't. And this would be true if we said, what if I had 100 data points? Well, it still doesn't matter. If we've already estimated our population parameter, then something has to be fixed somewhere. And so we lose a degree of freedom every time we estimate a parameter. If I estimate 2 parameters, I lose 2 degrees of freedom. But most of the time in descriptive statistics, we start off thinking about just losing 1, which is why we typically think of the degrees of freedom as n minus 1. It's also why in a lot of your sample formulas, you divide by n, because you're averaging something. In your population formulas, you divide by n minus 1, because you're still averaging something. You're just averaging it by the number of independent data points as opposed to the number of raw data points. So it's a little bit more refined of a measure in terms of being able to infer something to the population. So now let's go to variance and standard deviation. I remember one time in one of my first study groups, past multivariate, being asked to explain what is variance. And we all fumbled around and we were like, well, it has to do with standard deviation and it has to do with noise, and we came up with some what we thought were fairly decent things. And my professor at the time kind of chuckled and said, okay, so we don't really know. And then we started doing some little explorations with Excel. And I think it's fair to say that when we got done with all of those, we still didn't know. And so, but a few years later, we had sort of hammered it out to where we actually had a good indication of what it really is. So you might have noticed already, I kind of like illustrations, because even if they're not particularly representative illustrations, let's show it to me for real. Let me see the numbers work. Now, this data set is a real data set, but it is a very carefully chosen data set. So in my math classes, we used to do these exercises where we would measure people's height in inches, and then we would go back and we would compare it to other features like arm length or whatnot. But I actually chose these specifically to give us an average that was a whole number out of that real data set, so that we could focus on the concepts going on here rather than difficult numbers, and so that you would be able to follow the calculations reasonably well without having to sit there with a scratch pad and work through it. So if I add these numbers up and I divide by 6, I get that the average height of those 6 students was 66 inches. If I'm thinking about how good is that mean as a representation of these 6 heights, then it's a reasonable question to ask, well, what's the average distance of the data points from the mean, right? Well, the first thing to do then would be to find out what the distances are. And then I could add them all up, divide by how many ever there are, and I'll get an average distance. And that makes some sense, right? So far? So I add them up. I first off take the differences, and I just take each number minus the mean. So I've got -7, -3, 5, 1, -2, 6. Great. Let's add them up, and then let's get an average, and let's move on with our lives. -7 and -3 is -10. Adding 5 to that is -5. Adding 1 more to that is -4. Subtracting 2 off puts me at -6. And +6 added to that is 0. Oops. That's not going to work. Turns out I could have put any number in X, and when I put its average in there, in any amount of data points, by the way, when I put its average in there and I subtract the mean from those data points, they will always add up to 0. Now that's a proof that needs to be shown that I'm not going to show here, but there actually are ways to show it. But at least right now, I want to convince you of that fact just by sort of thinking about what we mean by a center value. For instance, if you go back to that original data set, here we go. If we think about this, here's my mean. I actually only have 3 data points above it, and I have 4 data points below it. Right? So it's not really in the center of the terms, and 50 is way higher, and so it's going to pull that mean from here. If 50 weren't here, that mean probably would be a lot closer to median, right? So my mean has been pulled away from there because it's based on the values of the terms, not where they lie, okay? So in other words, if it's not the mean, if it's the mean, this has to be 0. And if that sum isn't 0, then you didn't subtract the mean. Okay? You subtracted something else that you thought was the mean. Oh, it is true, by the way, if this were a long, non-repeating or non-terminating decimal and you rounded it, clearly you would not, in your rounding numbers, get an exact 0 here. But if then you got a computer to actually do it for you, you would. Okay, so we've got the mean difference here. And there's my mean again. And then I've got 3 differences. And so here's another illustration of why it would make sense that these numbers aren't the same, but when you start putting them together, they sort of have to be that 0. And that zero-sum problem is sort of what leads us to variance. It's not really a problem. It turns out this recognition actually kind of drops us off into the land of figuring out why things work the way they work to begin with. And we end up getting a whole world shown to us because of recognizing this problem. So it's actually a good thing that we have this problem, because if we tried to do these distances anyway, it wouldn't have worked to begin with. Okay, so let's just think about distance. We're thinking about average distance from the mean, so let's think about distance. Well, if you go back to your high school math, we typically think about distance formula, right? Well, the distance formula just says that between any 2 points, you really have this right triangle on a grid, and that if you take the A, the B, and the C, you can use A and B to figure out what the C is. But the first thing we have to notice is that A and B don't add up to C. This is a really, really important point, because if we had not realized we had a zero-sum problem before, we would have tried to use that one distance direct measure, and we would have basically fallen into a trap of thinking something like this. In other words, thinking that line C always has to be horizontal or vertical, right? Special case. So then we've got Pythagoras, which the distance formula is just the Pythagorean theorem reworked. Well, Pythagoras really wasn't about the lines of a triangle. He really wasn't about distance. He was about area. So what Pythagoras said in his famous theorem was not that if you took these two sides of the legs of a right triangle and worked my cool formula, you'll always figure out the length of side C. Actually, what he talked about were these squares that were built on a right triangle. So what he said was that the area of square A and the area of square B is related to the area of square C. So here's an illustration of this. Let's say that I took square A and I flip it across my triangle. I get two regions. If I flip triangle B across the triangle and include, I said triangle B, square B across the triangle, and I include square C in that flip, I get three regions. If I take those pieces of the area and I rearrange them, it matches exactly. And that is what is meant by a squared plus b squared equals c squared. It's not a cool formula for algebra. What it is a cool formula about areas. In other words, the area of the square plus the area of the square will fit perfectly inside the area of the other square. Now, that's where it comes from, and that's actually going to get us to variance really easily. But it does also solve this little problem for us, that we can find the side length now, right? Which was the whole point of what we started. We were thinking about average distance. Well, it turns out this is going to get us there. So I tend to think about square areas because if I talk about squares, people think about the four sides. And if I just say area, nobody knows what I'm talking about. So I tend to talk about the square areas, and we use them to calculate distance, and they eliminate this problem. So allow me to illustrate. We've got our distances. What if I square them? That would be the equivalent of taking that side length and building a square off of the side. And that's how big the area is inside of there. Notice when I do that, every single one of these numbers is now positive. So I can now add up and get a sum, which is how much square area is there in the system, total. Turns out when you run ANOVA, MANOVA, ANOVA, MANCOVA, any of those general linear model analyses. When you get an SS of something, it's that. That's all it is. I mean, they might have some funky way of getting to it and dividing out the groups, but conceptually, that's all that's going on here. Okay? That's not variance yet. That's sum of squares. In this case, this would be sum of squares of x. But I like pictures, and I think it's important for us to get an idea graphically of what's going on, because there are so many questions that come up when you get into the more advanced levels of these statistics and you don't have a nice set of 6 numbers. You've got a set of 20,000 numbers and you're working with factors all over the place. It's really hard to keep track of things. The better your basic pictures are in your mind, the better it's going to help you to where you're sitting in a conversation and people are going, well, why can't we do blah, blah, blah? And you go, because all we're talking about are sums of squares here. Let's not mystify this in any way, shape, or form that doesn't call for. So let's think about a picture. So I've got my same 6 data points. Here's my mean. I've got my distance to the first point, and I build a square. I've got my distance to the second point, and I build a square. Distance to the third point, build a square. For my negatives, I have distances also, which I've actually shown here as directions, right? Because the only reason that distance is negative when you subtract it is because they're below the mean instead of above the mean. But their areas still have space. And we have these 3 triangles. Now you might be thinking, as my wife once asked me, why can't we just use absolute value? If the distance being negative is all that causes the problem, why can't I just do absolute value and do an absolute distance average? Because A plus B doesn't equal C. Right? Because I still have the problem that those numbers don't actually add up to the real distance except in very, very special cases. Graphically, it would be the special case of a horizontal or a vertical line. And it turns out there actually are statistical theories built out of using absolute value to do some things. But my friends in the math department that do some of these assure me that they don't work very well. At least not for these kinds of things. Okay, so if I take these squares and I put them all together and I divide by 5, and why 5 and not 6? Degrees of freedom, you got it. Because 6 is how many I had in my sample, 5 would be, so 6 says, what's the average amount of noise around these 6 students' heights? 5 says, what do I think the average amount of noise would be in the population based on these? Okay? What do I think the average amount of noise would be around any 6 people that I took at that age and measured their heights? If I divide it by 5, I get 24.8, and that's what we call the variance. So one way of thinking about this variance is, it is the average amount of noise in terms of squared areas per person in the population. And if I had divided by 6, it would have been the average amount of noise or area difference, squared differences per person in the sample. Now, if I take that variance and I find the side length of that square, I get standard deviation. So you know variance is always sigma squared, and here's our formula with it. So this just takes all of our illustrations and puts them together with a sum of x minus x bar squared, all divided by n minus 1. That's our degrees of freedom. Your standard deviation is just the square root of that, the side length of that square. So I'm a little bit of a science fiction geek. and my wife rolls her eyes every time I do this, but the truth is that, and I deserve it, by the way, the truth is that when we're thinking about distances, we're thinking about a single dimension, right? When I square something, I'm moving to a two-dimensional plane. So basically, I call this dimension hopping. She's like, yeah, you would. But seriously, I've got this problem I can't get around. I've got a wall in single dimension world. So I jump over to a second dimension, past that wall, and then I square root back to the dimension I started in. It's dimension hopping. I think it's really cool. She's like, yeah, you would. Okay, so that's great. There's one variable. Let's move forward. Lines of best fit. Now we're into two variables. So we tend to think about linear regression or least squares regression when we talk about two data points. I'm sorry, two data variables, as many points as you want within the variables. The reason is that we need to have a reason for thinking it's something other than a line to move forward. So remember that among equations, you have lines are your first degree polynomials, then you have quadratics, then you have cubics, then you have quartics, and you have exponential functions that are not polynomials, and all these wonderful things. But most of what we see in life is linear. And most of the time, linear is the best description of that, unless we have a reason for thinking that it behaves in a quadratic function. So you all would have learned in some of your regression classes that there are times that we do things like quadratic regression. And that does make sense when you know that the system is that way, or that the data appear to indicate that it behaves something other than that. So the first thing is I want to do a quick vocabulary lesson. Why do we call it linear regression? Most people like line of best fit, and that's fine. But the reason we call it linear regression is because we're asking really about how far do points regress from a line. And regress, if you're not familiar with that terminology, means to deviate from. So a line basically ends up being the mean. So you got your single variable, it's your mean. You get two variables, the line of best fit is the mean for both variables. So when we talk about linear regression, just like we asked the question with one variable, how well do these variables, how well does this mean explain the variable? Now we're going to be asking, how well does this line explain the relationship between the two variables? And to do that, we want to again ask, well, how much noise is there around this line? So we usually start by considering the dependent variable. And the reason we start with that is because that's our outcome variable. It's our variable of interest. And its behavior is going to be, is really what we're interested in, okay? Whatever x is, that's our predictor to figure out what's going on in y, but what's going on in y is what we care about. So let's start with y. So here I made a data set up, and if we y bar of 4, we do our average difference again, we still get a 0, and again, here are our data points plotted on a line. But now here we have the regression from the line. And the mean y equals 4 in a two-variable system is just a horizontal line going across. So when I do the sum of y minus y bar, I still get 0. But basically now we're thinking about, instead of having one variable system with differences going left and right, we've got a two-variable system where distances are going up or down. So I basically sort of turned it so we could include x in this. And we can still build the squares off of each one of these just like we did before. We add them up, we divide by, in this case, 7, and we'll still get a variance, which we're going to do here in just a second. All the things that we just did for our first illustration of height still work for y. But we're going to pull x into it in just a second. But first, we're going to start with all of the things that we just did, and let's see where it takes us. So I've got an n equals 8, my df equals 7. So I square these and I add them, and if you see SSY in formulas, as just the sum of those squared differences. Which in this case is 48. So the average size square of variance, you'll notice that I like to put df as opposed to n minus 1, not because it is n minus 1, but because I like to remind people that I'm working with that we're really talking about the degrees of freedom here, and that there's some reason that it's n minus 1 in this case. Because in SEM, degrees of freedom doesn't stay n minus 1 all the time. But that's later on. So we take 48 divided by 7, and my variance then is 6.9. The average distance from the mean is 2.62. So basically I have a mean of, I don't see my mean up here. I forgot what the mean was on this. Was it 6 or something like that? 4, thank you. So I have a mean of 4 and a standard deviation of 2.62. Is that good? I don't know. It's just what y is. It's description. If I go back and I do the same thing for x, I still have an 8. I still have a mean, and this time the mean is 8. I do my mean differences. I square them. I get SS of x, or the sum of squared differences, sum of squares of x. Remember, those squares are built off of the differences. In this case, it's 56. So then my variance is 8, and my standard deviation is 2.83. Great. I just did, for a 2-variable system, all I've done so far is looked at each variable one at a time by itself. Now let's put it together. So I've got my x minus x bar, my y minus y bar. I've got my SS of x. I've got my SS of y. And now, because I put them together, I can get something totally new. So we've been talking about sums of squares. I tend to think of this one, the products, as a rectangle. Because there's no guarantee that the y minus y bar and the x minus x bar are the same. So if we're talking about squared areas up to this point, that's because we're squaring things. So they are going to be length times width are going to be the same numbers. But now they're not. And so we actually get a sum of products of xy, which is 44. We can then ask, how strong is this relationship? Well, the covariance of that number is just this product divided by n minus 1. So the covariance would be what is the average size rectangle of shared noise per person in my sample? In other words, how big is the noise that encompasses both x and y for each person? So there's a reason covariance and variance are very much related. Because in one term, we're asking, well, how big is the average size square per person? Now I'm asking, how big is the average size rectangle per person? And we also have this correlation that is also built off of SP, SSX, and SSY. If we take those numbers together, it looks like we have a correlation that's pretty strong, 0.849. From those numbers, we can estimate the line of best fit. We take we compute our slope. With the slope, we can then go back and use our averages to compute the intercept. And so we have a line of best fit now. And every time that you've ever punched a line of best fit into your calculator, that's what it does. And everybody says thank you, because if you've got more than about 5 data points, nobody wants to do this by hand. It's not even particularly fun doing it in Excel when you've got formulas to type in. Just hit the button, that's fine. But you need to understand that these numbers come from somewhere, and it comes from figuring out where is that noise and what's the average size noise, and then we've got ratios of the noises, the different types of noise to each other, to where we can minimize the amount of noise not explained. So I take this line, and now we have, this is the same data points. Before, this dotted line here is still our y mean. So before we had lines going down and up, and now we've got our line of best fit here. And we have distances from that line. In other words, how far do these points regress from this line? Well, it turns out we get this y hat. Y hat is, what are the values of y that we would predict based on our equation? So I take my x values, I plug them into this equation, what's the y value I get? And that's what we get. And I do the exact same thing again. Well, how much noise is there in this? And if I were to add these up, I'd still get 0. So if I square them again, I get 13.43. But notice, before we started this little roller coaster ride of doing the same thing multiple times and then combining them and doing them together, when we started with y, our sum of squares of y was 48. We have now reduced it by including x in the variables to 13.43. That's why we added x, because we reduced the amount of unexplained variance in y. Then we ask how much of an effect did it have? Well, we have our SS of regression, it's just 34.571 in this case, and the r squared, which, by the way, you would have also gotten this number if you had taken the r that we had earlier and just squared it, would have gotten you right back to this number, because they're all interrelated. It's all sums of squares of differences. Now, if you're sitting there thinking, this isn't advanced, this is very, very simple linear regression, you're absolutely right. It turns out that structural equation modeling is linear regression on steroids, because we actually draw all kinds of lines in an SEM model that every single line represents another linear regression equation. And so when I first started learning one topic, the professor said, do you all understand t-tests? And we all sneered and said, yeah, of course we understand t-tests, whatever. And then he started talking, and all of us were sitting back in our group going, I don't think I really understand t-tests. Then we had to basically deconstruct everything we thought we knew about t-tests, go back and spend, it actually took us about 3 months, almost a full semester of working through it before we actually were comfortable enough to sit back and say, oh, I think we understand t-tests again. And we understand it better than we thought we did before, because we understand what was wrong with what we thought before. That's what happens with linear regression here. And so a lot of times what happens when you first learn linear regression is, well, you've got two variables, and you figure out the line of best fit, and you get an r squared value for it, and you move on. And that's how good of a predictor it is. And that's not wrong. But it doesn't really, it's sort of like magic. Where did all this come from? And, you know, if you were lucky, then you might have gotten into a math class at some point that forced you to do at least 1 or 2 calculations. I actually was in a math class, my first stats class, that required us to compute the standard deviation by hand for data sets with 40 people in them. Now imagine filling out those charts with 40 people in 40 rows. It's long, and it's arduous, and it's tedious, and more importantly, it didn't teach us anything, right? I mean, all we were doing was, it was rote calculation. Okay, so in this column, I subtract the mean from the point. Great. Well, that doesn't take a lot of conceptual understanding to do that. So by the time we got done, it looked like, oh, they've got standard deviation. Yes, we can compute it. What does it mean? I don't know. But for structural equation modeling, you really have to start thinking about what does it mean, because you're going to be dealing with it in a lot of different places all at the same time. So that's why I wanted to make that aside. And I hope that was helpful, and if it only reinforced what you already knew, then that's still probably an important thing to have happen. Okay, so structural equation modeling. Let's get out of the review. Causal processes, and I've got causal marked big time here for a reason. I'll talk about that in a second. They can be represented by structural equations, which are just regression equations. They're just dependent variables being predicted by independent variables. And so a model of these relations can be generated and be modeled pictorially. So this is sort of how we draw a very, very basic structural equation modeling. So remember from, well, if you weren't here, you won't remember this, but if you were here, remember from the first session, and for those of you that are new, structural equation modeling starts from the premise that, let's say that I have 5 variables that measure self-efficacy. I've got 5 questions for you on a survey. And each one of those is going to measure some facet of self-efficacy. Then it doesn't make sense. I don't care about the answer to question 1 or to question 2 or 3, 4, or 5. What I care about is that underlying factor that nobody can see that we're calling self-efficacy that binds all 5 of those questions together. What structural equation modeling does is it actually works with those underlying factors and measures them and puts the emphasis on those rather than the observed variables. So you'll notice here that we've got little rectangle, well, there's squares in this picture. Those would be our actual observed items. So these are the questions on the test. These are the interview questions on the survey, whatever. These ovals then are the factors that they're trying to measure. The reason the arrow goes out from them is because, yes, it's true, we're going to do an estimate of this value from these, but conceptually, these items are emerging from that factor. And that's the way the models actually end up getting built. These are the error terms. So if you haven't gotten it in your head already, it's probably a good time to start remembering that errors in statistics do not mean mistakes. Errors in statistics are inevitable because it's the error of what you see versus what you expect. And there will always be a difference between what you see versus what you expect. So in other words, when we go back to that linear regression equation, remember that there's always a plus E sub I over here, or whatever variable you use to model it. That is, it's actually this plus error. And that error, in this case, are those little red arrows pointing out the points deviating from the line. So that's what these are, and that's what these are. That's what these are, and these are. You'll notice that I've got X variables here in the system, and I've got 7 Y variables in the system. And there are actually 2 factors under the X's. So these would be independent variable factors, and these others over here, these are keys. A little sort of squiggly cursive looking E is a Greek letter XSI, which can evidently be pronounced like 5 or 6 different ways. But we've always used key in my studies just simply because there's another variable that comes up later, that PSI, that is also pronounced psi. So to avoid confusion, we chose one that was different than the other. And there doesn't seem to be any sort of agreement. It just depends on where you are, how they pronounce them. But these typically are used to represent, to label the independent variable factors, and etas are typically used to represent dependent variable factors. And then you've got some other letters over here that are on these arrows. Those are slopes. And every single arrow here is a regression equation, linear regression. Okay? So I sort of went through most of this just now. So you've got X's or Y's, you've got latent variable factors. They're not directly observed. You've got exogenous ones, which is sort of the independent variable, and endogenous are sort of the dependent variables. So here's another way of thinking about what that looks like. So you've got latent variables that are not being predicted by anything in the model. You've got latent variables that are being predicted by something in the model. And then you've got your observed variables. Factor loadings is another name for slope. and your residuals and your errors are both just different forms of an error term. Okay. So then let's go back to factor analysis for a second. When we start thinking about underlying factors, one of the first things that you learn in multivariate is factor analysis. So why can't I just run a factor analysis and move on? Well, there are actually two types of factor analysis. There's exploratory and confirmatory. And confirmatory is what we're trying to get through today. Exploratory is what you would do in SPSS. So for EFA, there are several methods: principal components, principal axis, unweighted least squares, generalized least squares, and alpha. All five of these basically look at a different way of divvying up the variance in the model to make it make the most sense. And this is just sort of a description of what each one of those is. And the most common two that I've seen used for EFA are the top two. You have to have a very special data set to do one of these others. Like, there has to be some reason that you would do something other than PCA or principal axis factoring. Principal axis factoring was at one time just, it was like the first one. Okay, then there's maximum likelihood estimation. We're going to pause on maximum likelihood for a second, because maximum likelihood is one of the more robust systems that has come out for estimation. And so basically it looks at population parameter values based on observed data that are most likely to have arisen. In other words, it uses probabilities, which you would sort of guess from the name likelihood. The likelihood function quantifies the discrepancy between the observed and the model implied parameters. In other words, well, I'm going to show this to you again. I've got my data set. Here's what I'm seeing in this data set. Now, if my model is set up the way that it's supposed to be, then here's what I get with that. How different are they? So it's looking at a discrepancy. These models get extremely complex, and there aren't any closed forms for these. So closed forms meaning there's an equation, you solve it, you get an answer, and you move on. Instead, we use what are called iterative algorithms. And so we run it once, we see what we get. Based on what we get, we say, well, let's try to do this a little bit better. And we change our parameters a little bit, and we run it again, and we see what we get. And we change the numbers again, and we do it again, and we do it again, until we get the quality measure small enough that we're saying, we've got this. We're getting a little small enough change from this now. This is our solution. Okay. So let's let S be the sample variance covariance matrix. So S is going to be our observed scores. Sigma is going to be the variance covariance matrix of the population. So theta is the vector of model parameters. So sigma, based on theta then, is the variance covariance matrix that's implied by the model. So in other words, here's the way we think it runs. If that's the case, here's what would happen. Okay? And we're testing the hypothesis that that matrix holds in the population. So our null hypothesis then is basically that sigma, the population matrix, is sigma theta. So then SEM computes a minimum discrepancy function, which is called fmin, which is not the F value that you get with general linear models. So this is not the F distribution statistic. Okay, when you're running ANOVA or Mancova or any of those, you'll get an F value. That's not this. So it's not the minimum of some F statistic out there somewhere. Fmin is just the name of the minimum fit function. And F-min looks like this. The first time that my group and I saw this, we all went, "Ah!" But it turns out it's actually not so bad once you get the definitions down and kind of see what it's doing. So a trace just means the sum of the diagonal of a matrix. So if I've got a square matrix and I've got numbers going down the diagonal, I add them up. That's the trace. So if you take S and you take sigma theta inverse, the inverse times itself should give you an identity matrix. So just like if you took a reciprocal times a number, you get 1. If you take a matrix times its inverse, you get the identity matrix, which would be all zeros except on the diagonal you'd have 1s. So as my model implied sigma approaches S, then the product will approach I. As a result, trace will approach the number of observed variables. If they're all 1s, then the sum, the trace, is just P. So then if I take that minus P, this whole piece should be 0, or it should approach 0 the closer these two matrices get to each other. The other two pieces, if these are the same, then their logs should be the same, and they should approach 0. So it's basically two different ways of looking at how close are they. So that's the F-min function. And most of your fit indices in structural equation modeling are based on F-min in some way, shape, or form. Well, that was a lot easier to explain than it was to figure out. Okay, so maximum likelihood. There is this idea of a multivariate normal curve. There is no reason for you to be worried about this equation whatsoever. It's basically just the equation of a normal distribution. So the reason I show it all is that if you take an individual person's vector of scores, that puts them somewhere in this multivariate normal distribution curve. So what maximum likelihood is doing is saying, okay, based on where you fell in that curve, what's the height of the shape at that point? That's your maximum likelihood. So then the model's final parameters are those that yield the model implied variances and covariances and means, in some cases, that maximize the combined likelihood. So in other words, if you take every person's data set and you give them a likelihood score based on where they fit in this function, you do a product of it, you get the combined likelihood. From that combined likelihood, we take the log of that, and we get something that we refer to just as LL, or the log likelihoods. So the reason is that these numbers are very, very small, like starting with 5 or 6 zeros before you even get to a number. So the log of those was going to do a little bit more, I don't want to say it linearizes it, but it does make things manageable. So then when we get the sum of all of the log likelihoods, we've got something again that I'm not going to go through all of this because it's not that different from the logic of F-min. Although you're not actually, it's not set up to give you 0, but it's basically just a formula that says, here's what the likelihood is, the log likelihood is of all of this. Okay, so with complete data, each person has the same contribution to the log likelihoods. In missing data, it actually can deal with this really well because it just takes the data that you have for that case and it doesn't give you credit for what it doesn't have, and it doesn't take away for what it doesn't have, and it doesn't lose what you have. It's just, here's my number of data points and here's how many it contributed, and so that's what its overall contribution is. Which makes maximum likelihood not only really nice to use with complex systems like structural equation modeling, but it also helps us deal with bias and missing data. Okay, so once we get all of this, we get an aggregated log likelihood, and we don't have any imputed data because we didn't need to for maximum likelihood. Is full information maximum likelihood, which is just maximum likelihood. There is an REML, which is restricted maximum likelihood, which is better for small number of sample sizes, which we never use in SEM. Okay, so then all of the parameters and their standard errors are estimated directly using all observed data. And maximum likelihood is the default in most of our SEM softwares. And the big two, there's actually several, but M+ is probably the biggest one right now because it's just so versatile and can do so much. And it's fairly straightforward in its logic. AMOS is much more graphical than most of the other softwares, but it's a little bit limited in some of the things that it can do. There's another one that I haven't listed up here, Listral, that it'll do a lot. It's very, very powerful, and it's one of the first softwares. It's also Fortran code based. So then there's EQS, and there's a bunch of other ones out there. M+ has sort of emerged as the leader because it does all of these things for SEM, and it also does software for item response theory. It does stuff for very, very special cases and weird data sets that we don't even need to go into. So it's become sort of the package of choice. And it does that maximum likelihood by default. So confirmatory can't be run in SPSS particularly easily because you can't force the variables to load on any particular factor. It just takes the variance and it sorts it out by the different criteria that you chose, and there they are. In confirmatory factor analysis, we already have a sense that variable 1 goes with this factor. Variable 12 goes with that factor. However, SEM software accommodates that easily. So here's an example of a first order CFA where we actually had, from the BSI 18, different types of symptoms of depression, and we had different types of symptoms of anxiety. And so so every one of these arrows is a regression equation. And then we had, and it's basically just item 37 equals the slope times depressive symptoms plus its error. And then you just keep going down through that. And that becomes your matrix of your model implied, that theta matrix. Okay. We also were able to do what was called a second order, where we said, what if all of these are just part of one psychological distress factor? Turned out they were not. The data, we tried it like 15 different slices, and there was just no way that it ever, the best we could come up with was that it only made the model worse slightly. And so this, no. So, and there's a lot of reasons for thinking that might not be the case anyway. So this is the kind of picture that you would put together, and this is very clear that item 37 is not an anxiety symptom, whereas in exploratory, you don't have any choice over that. Okay. So there are fit functions. And based on this is just some of the variables. You'll notice, like, for example, RMSEA, the root mean square area of approximation, you want a smaller fit because it's measuring misfit, basically. It's measuring residual. And so less than 0.05 is considered a good fit. And in this case, we only had a 0.071. So we actually fit into that reasonable range, which I'm told is really good in this field because the measures are not particularly reliable. So being able to get something that strong was good. You got a 90% confidence interval here that actually gets us pretty close to the good fitting range. And then the standardized root mean residual was very much into the good fit range. When we got done, this is an example. You'll notice that there are numbers all through here. These are our parameter values. This includes our errors, our slopes, our variances, our covariances, and the standard errors of each of those. So then, one of the things that I'd like to kind of leave you with today is just a quick reflection on some of this. So we've been thinking about linear regression, and we've been thinking about how that builds to a structural equation modeling, and how structural equation modeling lets us do this confirmatory factor analysis. And I think it would be worth thinking through on your own a little bit about, well, what is your conceptual framework? And if you're not working on a dissertation or a thesis, that's fine. What study are you working on right now? What is the conceptual framework? How do the variables align to those things? Are they well measured? And are they well established? It's a whole study by itself testing, here's what people think this is supposed to be done, how this works, here's what we found. So I've actually got a study that's going on its third grant and is on a proposal being reviewed right now, 5 years, 6 years into this study, that we really started with how do mathematics misconceptions really work? And everybody thinks they should be done by, well, you have algebra misconceptions and geometry misconceptions. And it turns out that's not how it works at all. And the way we got there was to start with CFAs. So, so kind of some interesting stuff. So I believe that puts us at the end of our time for today. Yep, we're there. So thank you to everybody who was on the webinar, and thank you to everybody that was here today. We will be, this is the last of these sessions that we'll be doing this fall. Our next ones, I think, are the first one's in February.
Yes.
Right. And so we will be picking up with this, and we'll be talking a little bit more about what you do after CFA and models that aren't just confirmatory factor analyses, and dealing more with getting into that causal process that we sort of hinted that there's more to it than that, but we really didn't get into that today. So there's a lot to pick up on from there, and we'll be here at the same place in February. So have a wonderful rest of your semester, and we'll see you next time. Thank you.
Thank you.